Hello, good evening, and this is Professor Khan, and this is week 2 of EST-205 Advanced Heat System Design. And this week we will discuss the following subjects. Hold on, let me get to them. Here we go. So we will talk about heat transfer modes and their functions. That's something we already addressed in the EST-204, which is the types of heat transfer and how do we transfer heat from one location to another. We will also talk about heat transfer fluids used in HVAC, and probably you'll see more details in the book in chapter 2. Location for heat loss in a building. We will also recognize the heat transmission requirement. That being said, is we try to, hold on, get my pen. We'll talk about the components of the equation Q equal A times U times delta T. So I'll talk about these components. What do they mean? How do we manipulate this equation to solve for one of those variables, if they are variables. And finally, we'll talk about heat loss through a wall. That is conduction, of course. And we will also address the need for insulation and how do we calculate for the proper insulation. Okay, let's get on with it. So heat transfer modes, we know about conduction, convection, and radiation. Um, we did talk about that a little bit last semester, but we will reiterate now. I'll talk about conduction, convection, and radiation. We know that conduction always through a solid. Convection is through fluid, be it gas or liquid, and can be either free convection or forced convection. So the free is when we use buoyancy, that knowing that hot air rises and hot fluid rises and cold air sinks. So that's free convection when we have the air circulate by itself, or we can use forced, and that is when you have a fan or a pump. Okay, radiation has no medium. Radiation goes through vacuum. It goes through space, and basically it's a frequency. And we did talk about frequency and how higher frequency tend to travel faster, and we did some touch base on that in the last week material. Okay, so what do we need to know? Why do we need to know these things? Well, first of all, we want to have conservation of energy. If we know where the energy is going, we can know how to mitigate that direction and reduce the heat flow from one place to another. So basically, we're trying to be a little bit conservative with the energy that we are making in the basement, in our boilers, furnaces, and have them go in the right place, which is the living space. Again, limiting heat loss. Also, we can utilize these means to transfer heat to our advantage. We want the heat eventually to move from the boiler, the radiator, to the air to warm the location where we're staying. So it's the purpose of heat transfer is to mitigate heat loss and also utilize better utilize heat where we need it. Heat distribution is another thing. If we understand the basics of heat transfer, we can have a better heat distribution. And I can't stress the fact that these are really vast fields of science, and people spend their lifetime um, trying to better understand heat distribution, heat transfer from one location to another. It might seem like a very small subject to you when you do residential heat loss, but it gets a little bit more sensitive when it comes to higher equipment. Complicated equipment or big buildings where you have to transfer millions of BTUs from one building to another. Think about our campus, for example. We have a boiler that is producing millions of BTUs in one building, and this heat has to go all the way to other buildings. So the bigger the system, the more sensitive these things become. Okay, so again, going back to the review, we use convection, either forced or free. And for convection, we can use fluid. Either for us, we use either air, water, glycol. Sometimes we use synthetic oil. Sometimes we use different kind of blends of fluid that can transfer heat. So for us, we do use air in forced air systems, and we do use water in hot water systems. Sometimes we use glycol or a blend to in heat in a hot water system as well. For steam, we use water. You cannot put antifreeze in steam system. So what about non-fluid transfer? That's also called conduction. We can have material that are good conductors to transfer heat from one location to another and can do some good transfer mesh through the floor, through the wall. I'll give you a quick example. For geothermals now, there are something called the graphite rod. Graphite is good material to conduct heat, and there is no, it has good properties that will conduct heat in a way that it does not concentrate in one area or one spot and distributes very evenly and quickly. So these rods have been used for geothermal, where they will dig a hole deep in the ground above 30 yards, where the temperature is stable, and they insert graphite rods. And again, there's a lot of ongoing research into what material we can use for heat transfer that will take the heat for uh, long distances without being lost. Also, the shape plays a big part in that. I'm not going to go too much into it, but we can also distribute heat using solids, uh, just as convection. We can use irradiation as well, but radiation can get blocked. So if to transfer heat through radiation, you need an open space or a moving medium. Once you how do you block radiation heat? Think about your car. You can block radiation coming from the sun just by having a reflective surface. That's it. That will block completely the radiation coming into your car. So it's it's not a very effective way to transfer heat in a building, but it has been used for many other means of heating and cooling. Okay. So heat loss in a building, we did talk about that a lot. We have infiltration and transmission. So infiltration happens through holes in the building. We can perform a blower door test to test for infiltration. It is required to have some heat exchange, and some air exchange from inside the house to the outside. This can happen usually through natural or mechanical means. However, ideally, you want to have a very tight building, and you want to introduce your own air coming into the building. That gives you more control of the quality of the air instead of depending on the infiltration into the house. So we did talk about that again in chapter 4 last semester. If you still have the book, probably you can look over that. Transmission, it's basically having the heat going through a solid medium. And they're not always completely solid. There are some pockets of air in them, so it can be either or. So you can have transmission through walls, windows, floors, doors, and ceiling. And this is actually what we did last semester for the heat loss project, where we did the heat loss calculation for all these mediums in the rest of the Excel sheet, and we'll go over it again next week or so. Okay. Again, continuing on heat transfer, we're talking about transmission again. We need to know the material. That's why we have to go and look at the U factor. I hope you still remember that. So the U factor depends on the resistance, which is 1 over R, and the resistance depends on something called K, which is the thermal conductivity of the material. And I told you, we don't have to think about that a lot, as long as you know that U equal 1 over R, and of course R will equal 1 over U as well. So we need to know the material, that's the U factor. The heat transfer law, I hope you know it by now, which is Q equal A times U times delta T. I keep repeating myself, but I want you to remember this simple law because we will use it a lot in different variations. And then again, delta T is the indoor and outdoor temperature. What is the temperature difference? And you will notice again that the higher temperature difference you have, the higher the rate of heat transfer. So more delta T, more heat transfer. more area, more heat transfer. U, again, more U, more heat transfer, but again, more resistance is less heat transfer because it's the inverse. U is the inverse of resistance. Okay, so I'll give you an example of how to calculate insulation requirement. So I'm assuming that you have, since all of you have done the project from last semester, that you understand how to do heat loss through a wall or a window or a door. So in this example, I would like to take you a little by little into how to add insulation. And again, this is something we did last semester, but I want to do it again in more elaborate form. So if we have this example, we did a heat loss calculation in a room, and we find there is a heat loss from the wall facing the outside by 3,240 BTUs per hour. The room has only one wall facing the outside. This is the area, 8 by 15, and this is the U factor. We went to the H22 book and we find the U factor be 0.45. And this is the temperature difference. Inside is 70, outside is 10 degrees. And we would like to know what are our options that will lead us to reduce the heat loss or heat transfer by 50%. And is it doable? So let's take a look first. If we were to do the heat loss equation, we will get this number. So this was a result of these three multiplication. The area is 8 by 15, which is 120 feet square, and delta T is 60 degrees Fahrenheit, 70 minus 10, and U factor is given from the book as 0.45. These are given. So going further, if I want to take 50% out of this heat transfer rate, that's kind of easy because 50% is half. You go and divide this by 2, and this is half of this percentage. So it's a little bit easy because it's straightforward. And if you think about the equation again in here, just right off the bat, if I want to reduce the heat loss by half, what can I do? I can change the area. That's already given. I can't change the delta T because that's again a given. This is what I need inside and this is what's outside. I can only change the heat, the insulation. And so basically if I cut this by half, I'll cut the entire thing by half, which means I need to double the insulation. That's really simple. But if you want to do it mathematically, here you go. So this is the resistance of the wall, which is 1 over 0.45, which is 2.22. This is the equation I gave you last week, and it's I did an example on it also on Blackboard. The equation is given at the end of the book. So you just substitute all the variables here, and if I substituted, I got 2.22 for my resistance. What does that mean? If the R wall is 2.22, why am I getting the same number here? Is this some kind of a trick? No, it's just because we said for us to reduce the heat loss by 50%, we need to double the insulation. So that means the insulation for the wall and the added insulation will be 4.44, double what we have. Okay, take a look at it, please, and let me know what you think. So here's an example that I want you to pause now and do this on a separate paper. Take your time, try to look at it. And here's what we have. We have the heat loss calculated already. We have our area. We have our U factor, temperature in, temperature out, and I want a reduction in the heat loss by 80%. So I want to reduce it by 80%. So I want the new heat loss to become 20% of what it was before. So let's say 80% discount in heat loss. So pause the video, and I want you the insulation required is going to be 11.6. Try to work your way through it. Give it like 5 or 10 minutes. If you don't, it's okay. Come back and rewatch the video. I'll go over it step by step. But okay, I'll see you in 10 minutes. Okay, hopefully you got that number. If you did not get that number, then this is how you do it. This is going to be, this is our heat loss, right? And it's all the criteria from this that we talked about before. And let's take it first. We have our heat loss. We want 80% reduction, which means you're going to multiply by 0.2, which is 20%. So this is my new heat loss, which is 3.304 BTU hour. So if you don't know how to calculate percentages, think of buying clothes or going to discounts and they tell you this shirt is 30% off. What does that mean? So you're going to take third of that price, 30% of that price and knock it off. So it's the same thing. This one is 80% off. So what you will end up with is 20% of the value. A lot of calculators will do that kind of discount for you, but if you don't, I'm going to go over it a little bit. There are 3 ways to do it mathematically. Whatever is easier for you, just use it. We have the area, the U factor, and getting the R from the U factor to use in our equation. This is the equation that we described before. Here's me putting all the numbers, and I did. This line is annoying. Okay, here's the equation. So substituting all the numbers and the new value for U, we will get 11.6, which usually R12. You're not going to go to Home Depot or Lowe's and buy 11.6 R value. You need 12 R. So hopefully this makes sense a little bit. Give it some time to get all, just to fill in the blanks and the variables, understand how this came from. And well, if you need, you can rewatch the video from week 1 in doing insulation. Here's an example of how to do percentage. If we want to think about deducting percentage, if 100% is complete one, going to fraction, and 50% is 0.5, so 38% is 0.38. It's just changing from percentage to decimals. Okay, so if you would like to have the remaining value of whatever fraction you're going to take out, so you have 1 minus the fraction. So example, if you have 3,000 minus 30%, 30% is 0.3, so 1.1, complete 1 minus 0.3 will give you 0.7. So if you multiply 0.7 times 3,000, you'll get 2,100, which is 3,000 minus 30%. That's one way to do it. Another way, you can go directly and deduct by whatever you have. So it's like you say 30% is 0.3, that's 900. Then you subtract 3,009 minus 900 and you can get 2,100. If you find this a little bit confusing, most calculators, and you can use your calculators, have a percentage function in it. So you can say in your calculator 3,000 times 330, then you hit the percent button and they should give you that number. So practice it a little bit, find the way that you can do it, whether it's calculator, application, Excel sheet. I just need to understand what does it mean, because it will make a big difference. Okay, there's another example here, and again, it is worked out. I will let you practice that on your own. But in this example, I tried to find the U factor from the same equation. So this is my main equation here, times U times delta T. And in this case, I did not have the U factor, and I want you to manipulate this equation to get the U factor out of that. So I used, so U factor in here will equal, if I would like to rework this equation, will equal Q divided by area times delta T, which is what I did here. This is the Q over delta T times the area. And this is, I found my U factor over here. I get the R from the U factor, which is 1 divided by the U. And I found my new heat loss, and I substituted that in the previous equation that we saw to find out that the insulation should be, again, almost to 1, a fraction which is like 60% or 0.6 to reduce the heat loss factor by 40. So I hope this makes a little bit sense for you. And what I did here is just manipulated the equation to solve for the U factor instead of solving for the heat loss. Here is a website that actually shed some lights on the idea of insulation. Do we always want to add more and more insulation? Can we just like go and buy, I don't know, tons of insulation, just put it in there and should be, is that better? Again, first of all, insulation is costly. Installing insulation is costly. So go check out those YouTubes and see installations and why is it important and is it always better? The short answer, no. There's a limit where installation makes a difference, and after that it's just a waste of money. And let's do the math to think about that. So if we were to use this equation, and this is my insulation, which is 1 over R total of the wall, and again I'm solving for the Q and insulation, the added insulation over here. So this is how we get that equation again, just going through the steps. And what I did in this example here is I kept the temperature difference constant, and the resistance of the wall is not going to change. It's always going to be the same, and the area of the wall is not going to change. So I kept those three things constant, and look at this equation that has the calculation of the heat loss factor, and I kept adding insulation in an increment of 0.5. And as we can see, the heat loss of course keep dropping, but at some point the drop is not significant, and you can notice that here is so insignificant. Meanwhile, I'm adding insulation, and let's say even if each layer of insulation is $1, that's still a lot. So, and to find the sweet spot here, that's around 3 R3. Any more than that and you're just wasting money and space. And to put this graphically here, I plotted those data, and you can see you drop in terms of heat loss until you reach 3. Then after that there's a drop, but it's always almost insignificant, and the amount of insulation is getting really ridiculous now, so there is no need for that. So this is just to show you that, and hopefully you can make use of it in the future, that to convince somebody that insulation is not going to be always a good idea. But you can also, doing that, you can find out at what, you just don't have to do all this data, all this math. Just try, calculate the heat loss at 2 and the heat loss at 6, and see if that will make a big difference, especially when it becomes more expensive and the space is tighter. Okay, so I know I threw a lot at you this week. This is the basic things that I want you to remember from this lecture. First, heat loss through a medium, either convection through fluid or conduction through solids. The rate of heat loss is a function of, first, insulation. The more insulation, the less heat loss you will have. Surface area, more heat loss. Temperature difference, higher temperature difference, higher heat loss rate. Your house could be doing very well in the fall, very well in the early winter. By the midwinter, when it's really cold and it's 0, you might see a rapid heat loss through your wall. So again, it's a function of the temperature difference. Where is the heat going and where is it coming from? That's something you have to think about. How much BTUs I'm making and how much BTU I'm getting where I want it to be and where this is going. Again, that's the first law of thermodynamics, which is conservation of energy. How to calculate required insulation. Again, let's not be one of those technicians who just suggest you to add more and more insulation. There's always a limit, and there's always a smart way and always an optimum way to insulate without compromising cost and also function. Again, we did answer this question. And cost of insulation versus heat loss. Again, it is costly, and it's good to know when to stop adding insulation. Okay, thank you for your attention, and please check out the Blackboard for discussion questions and homework, and post any comments that you might have about insulation into the discussion board. All right, see you next week.